In this video, we want to look at the relations between two sets or more. So by relations, what I mean is comparing the objects between sets. Comparing the objects between sets. Let's look at an example. Let's say I had a set A that had 1, 5, and 10 as objects. So all the elements in set A can be listed out like this. And if I had a set B that had the objects 10, 7, 5, and 1, and I list out all the objects in set B, then we're in position to start comparing the objects between sets A and sets B. So the first question is, what objects in set A are present in set B? Well, both the object 1 is present in both, the object 5 is present in both, and the object 10 is present in both. So we can see that all the elements in set A are also elements in set B. So we have exhausted all the elements in set A when doing this comparison of which objects are in what set. And because all the objects in set A are in set B, then we have a special relationship between set and A, which we call subset. So A is a subset of set B, meaning all the elements of set A are also elements of set B. So that's what subset means. And notationally, we say that A is a subset of set B. So this symbol just means subset. Is set B a subset of set A? So question, is set B a subset of set A? For it to be a subset of set A, that must mean that all the elements that are in B must be in set A. Now, we have 3 of the objects in set B that are in A, except 1. The object 7, while it is in set B, it's not an element of set A. And because it's not an element of set A, we can't have set B as a subset of set A. So it's not a subset of set A because set A is missing this object 7. So this was an example of two sets that just had numbers as objects. And what you can notice quickly is that the question is C a subset of set D, or is D a subset of set C? Or are both of them subsets of each other? Or neither? Okay, so for set C to be a subset of set D, that must mean all the points A, B must be of set C must be in set D. And the way we need to look at this is by the intervals we have for the values of A and the values of B and compare them to each other. Well, in set C, I could already tell that the values of A, specifically A equals 0 and A equals 10, are not in this interval. Because here we have A's between 0 and 10, but it doesn't include 0 and 10, while in set C, it does. And likewise, here we have B is able to equal 1 and 20, but in set D, it's not. So there are actually points in set C that are not points in set D. Specifically, those points are all the points where A equals 0 and we can have any value of B. So this point where 0 is represented by A is not going to be an element of set D. So isn't the point where A equals 10 and we have any value of B. This point is also not in D. Two more points that are not in D will be the points where we have any value of A and B equals 1. So this point is also not in D. And finally, the point A comma 20 is not an element of D as well. But it only takes one element to show that a set is not a subset of the other. Here we have 4, but we only needed to show 1. So set C is not a subset of set D because there is at least one element or at least one point in set C that is not present in set D. Specifically, there are 4 elements. But is set D a subset of set C? Well, in this interval, A is between 0 and 10, and here A is between 0 and 10 as well. So all the values of A in set D are in set C. Likewise, all the values of B in set D are in set C, because here B is between 1 and 20, and so is B here. We can illustrate set C and D on the xy plane. And if we just look at the first quadrant of the xy plane, so here's going to be our x and our y-axis. Our A is the x-coordinate, and we'll have A be between 0 and 10. So 0 will be here, 10 will be here. B is going to be between 1 and 20. 1 will be here, and 20 will be here. Let's put the 10 a little closer just to make the scaling seem reasonable. In set C, A is between 0 and 10, and B is between 1 and 20. And if we represent this as a rectangle, then this is how it would look. So the length of the rectangle will be 10. So let me pick a different color here. So the length of the rectangle will be 10. And then the height will be 20. Oh, 19, because 20 minus 1 is 19. So actually, our rectangle will start here, and it's going to go up to 20. And this is not the straightest rectangle. Let me try to make it a little better so we can see it. So this rectangle is set C, meaning all the points within this rectangle and on the edge of the rectangle, so on these edges here, are all the points represented by set C. And set D will look similar, except we don't want to include all the points on the edge. So set D is going to have all the points within this same rectangle, except it's not going to have points on these edges. So set D will look like this. So it's the same rectangle, except the edges are dotted because we're not including any points. We're not including any points on set D, on the edge of this rectangle. And because these edges don't count for set D, but they do count for set C, we could see how D is a subset of set C because these points are included in set C. And all the points within this rectangle are included in both sets. So D is a subset of set C. Let's take another look at an example with points, and it's going to be a little more tricky, but we'll also illustrate it just to see the picture. So if I had a set A that contained the points x, y, where we were looking at the positive square root of x squared plus y squared equals, let's say, 16, and I had a set B that was the set of all points x, y, such that we had the positive square root of x squared plus y squared equals 4. Oh, let's change these equals to inequalities. So I want them to be less than or equal. Then which set is a subset of the other, if any? So if you're saying that set B is a subset of set A, then you would be correct, because all the points x, y that make this inequality true will also make this inequality true. If we draw this on the xy plane, so I'll draw the xy plane, but before I do, maybe it's best to discuss what these equations represent. If you recall, an equation of a circle, a general equation, is going to look like this, where x and y are the values of the point, and h and k will be, the point hk is the center of our circle, the circle. So this entire equation represents a circle with radius r. So r is the radius. And xy represents the point on the edge or circumference of the circle. So in our case, we have, if we rewrite this inequality in this form, we'll see that our radius here is 4, and our hk will be 0, 0. So our circles for both of these sets will start at the origin. So for set A, it's going to be a circle with radius 4. And actually, it won't be a full circle because we're just looking at the positive of the square root. So it's going to be the top half of the circle. So that's how set A would look if this point was 0 and then this point would be 4, because then this would be the radius, which is 4 as well. So this is set A. Set B will also be at the top half of a circle, except its radius would not be 4, but 2, because square root of 4 is 2. So if we draw that top half, it would be about like that. Not the best drawing, but it's the best I can do. So this would be 2. And because of these inequalities, set A, so this is set B. Set A contains all the points here and on the border, on the edge of the circle, and it also includes points here because it makes up this entire top half. And what that means is all the points that are in set B are also in set A because the points of set B are also here. But none of the points in set A, well, some of the points in set A are in set B, of course, but some of the points are not, specifically this part that kind of makes a crescent shape. So this crescent shape and all the points within it are not in set B. So A cannot be a subset. So let me change colors here. A cannot be a subset of set B, but B is a subset of set A because all the points in set B are in set A. Now that we have a better understanding of subsets, let's look at a few interesting facts that we can do with them. So the first of them is pertaining to the special sets we talked about in the last video, which were the natural number set, the set of integers, the rational numbers, the real numbers, and the complex numbers. How would the relationship between these sets look like in terms of subsets? The natural numbers are a subset of the integer set, which is a subset of the rational numbers, which is a subset of the real numbers, and the real numbers is a subset of the complex numbers. And putting the subsets in this order also implies, for instance, that the natural numbers is a subset of the rationals. It's also a subset of the real numbers, and it's also a subset of the complex numbers. Likewise, the rational number set is a subset of the complex. The set of integers is a subset of the reals and the complex. So we have a nice ordering of these 5 special sets. The second fact is that picking any set, it must be a subset of itself. So set A, whatever this set is a subset of itself. So A is a subset of itself because it must contain the same elements because it's the same set. So whatever elements are in A, well, they're in A. So by definition, it's going to be a subset of itself. And the last fact has to do with the empty set, which was the first special set we talked about in the last video. And the empty set is a subset of every set, which is fascinating. So you could pick any set and you'll know for certain that the empty set is a subset of every set. So why is this true? We can outline a proof here. And we will do this by picking an arbitrary set called A. So let A be any set then I could make a statement such as this. So if I pick an object, a value, a point, whatever it happens to be, if this object X is in the empty set, then this object must also be in this arbitrary set that we picked. And this statement happens to be true. But why is it true? Well, my hypothesis that if X is in the empty set is actually a false hypothesis, right? Because we know that the empty set can contain no object at all. But I'm supposing that there is an object in the empty set. So because this is a false hypothesis, when your hypothesis is false, it doesn't matter what the truth value of your conclusion is. It could be false or true, but when your hypothesis is false, that makes your statement, your if-then statement, true. So because this is true, we actually have proven that the empty set is a subset of every set because we show that if there was an object X in the empty set, then that same object must be in this arbitrary set we picked. And again, that's true because our hypothesis is vacuously true. That is, it's false. And because it's false, logically speaking, that would make the whole statement, our if-then statement, true. So that covers everything we need to know about subsets. The last relation we should talk about is the equality relation. What does it mean when two sets are equal? So equality. When are two sets equal to each other? And to answer this question, we actually will use the subset relation to help us. So two sets A and B are equal if and only if A is a subset of B and B is a subset of A. This if and only if statement means that if we have this, then this is true. And if we have this, then this is true. So if A is a subset of B and B is a subset of A, then we'll have that A is equal to B, which is pretty neat. So for example, if I had a set A containing -3, 0, and 4, and I had a set B containing the objects 0, 4, and -3, and because we have that A is a subset of B, since all the elements of A are in B, but we also have that B is a subset of A because all the elements in B are also elements in A, right? So the -3 is present in both the 0 and the 4. So because they're subsets of each other, we can conclude by this definition of equality that A is equal to B. And this definition of equality is great because it just requires that they have the same elements. It does not require that the objects in the sets be in the same order, right? So here, the first element in set B is 0, and then it goes to 4 and then -3. But here, we start off with -3, and then go to 0 and 4. So even though the order of the objects is different in set A and set B. It doesn't matter when we talk about the equality between the two sets. It just matters that we have the same elements in both sets for them to be equal, which is pretty neat. So another example we should look at is when we have a set A that contains an object that's another set. So let's say it contains a set that contains these objects, and then set B contains these objects. At first, it might look like they contain the same elements, and then we could say that A is equal to B. However, if we take a closer look, set A only contains one object, which is this set, which is an element of A, and set B contains three objects. And if we compare the objects of B and A, we can see that actually neither of them share any elements in common. So A cannot be equal to B because none of them are subsets of the other. And similarly, when we had this fact that a set A is a subset of itself, that must also mean that a set A must be equal to itself.